Welcome to the Explainer. So today, we're going to completely shift how you look at conic sections. If you've been pulling your hair out over endless lists of equations and properties, take a deep breath. We are tossing out rote memorization and building pure visual intuition. By the time we wrap this up, you're going to see the hidden mathematical DNA that perfectly connects all these fascinating shapes.
Okay, here's our roadmap for today. 1. The blueprint of conics. 2. Anatomy of the ellipse. 3. The hyperbola sign flip. 4. The great mathematical divide. 5. Targeting the exam heat map. And 6. Surviving 5 common trapdoors. Let's dive right in.
Section 1, the blueprint of conics.
Now, this right here establishes our core duality. The ellipse? It's built entirely on a constant sum of distances to the two foci, but the hyperbola relies on a constant absolute difference. Think about that for a second. Just changing one single word from sum to difference literally alters the entire physical reality of the curve on the graph. To understand exactly how we mathematically morph between these very different shapes, we first have to define something called eccentricity, or E. It's basically a strict threshold that dictates the curve's identity. You can think of it as a measurement of how much our shape deviates from being a perfectly symmetrical circle. Watch this threshold in action, it's pretty wild. When eccentricity is exactly 0, we've got a perfect circle. But as you start sliding that E value up, so it's greater than 0 but still less than 1, the shape stretches out into this beautiful elongated ellipse. And here is the magic moment. Right when E hits precisely 1, it breaks open into a parabola. The second it exceeds 1, it completely fractures outward in 2 opposite directions and becomes a hyperbola. It's all one continuous mathematical evolution. Section 2, Anatomy of the Ellipse. Look at this perfectly bound, closed loop. The ellipse is really a shape of restriction. Those 2 focal points, the foci, they're securely held inside those gentle curves, completely locked in by the major and minor axes. Literally everything about this shape screams containment and balance. Because of that containment, the crucial mathematical anchor here is the master key equation, a squared equals b squared plus c squared. This simple Pythagorean-style relationship perfectly governs the proportions of the whole closed system. It tells you exactly how the major axis, minor axis, and focal distance play together to keep that loop tightly shut. Section 3, the hyperbola sign flip. But what happens when that perfectly closed loop finally breaks open? Compare the bound shape we just looked at to the hyperbola. Notice how the geometry has essentially been turned inside out? The bounded loop fractures, creating these infinitely expanding branches. Those foci that were trapped safely inside are now sitting on the outside, pushing the curves infinitely away. And you know what? This physical fracture is perfectly mirrored by a fracture in the math. Notice the DNA swap here. For the ellipse, a was the biggest value, right? Hence, a squared equals b squared plus c squared. But for the hyperbola, actually, scratch that. C is the one that takes over as the biggest value. The focal distance dominates, so the new master key becomes c squared equals a squared plus b squared. It's just a simple rearrangement of addition and subtraction, but it completely redefines the geometry you're dealing with. In fact, if we look at the standard equations, it's all driven by one critical sign flip. Just changing the plus sign in the middle of the ellipse's standard form to a minus sign, that mutates the entire curve into a hyperbola. You aren't learning 2 completely different subjects here. You're really just learning what happens when you flip a single mathematical switch. And what's wild is that despite fracturing wide open, the hyperbola doesn't just fall into total chaos. Instead, as it expands out toward infinity, it perfectly hugs this invisible architectural scaffolding we call the asymptotes. These straight diagonal lines act as strict guardrails, dictating exactly how the hyperbola expands forever. Section 4, the great mathematical divide. Okay, this table should absolutely be your aha moment. You do not need to memorize 2 separate massive lists of formulas. You just need to learn one set and apply those critical sign flips we've been talking about. Look at the relation row, just a quick flip of the plus and minus. Look at the tangent condition, a squared m squared plus b squared for the ellipse minus b squared for the hyperbola. Seeing this parallel symmetry? That is the secret to literally cutting your study time in half. Section 5. Targeting the exam heat map. Now, let's shift gears from theory to straight-up tactics, because at the end of the day, you've got an exam to pass. You have to treat your study time like a highly precious resource. Look at this heat map for advanced exams like the JEE.
It visually proves that, hey, not all formulas are tested equally. That bullseye right in the center, that's where examiners spend almost all their time trying to trick you.
To use this effectively, you've got to practice steady triage. You must ruthlessly prioritize the red zone. We're talking tangent slope conditions, eccentricity derivations. These are your absolute non-negotiables. Once you've mastered those, then you move to the orange zone, things like asymptote geometry. Only when those are perfectly locked in should you even think about the niche blue zone topics. Section 6, Surviving 5 Common Trapdoors. Here is the harsh truth, though. Even with the perfect focus, exams are absolutely loaded with traps designed to catch you off guard. Trapdoor number 1 is the classic C-squared mix-up. Under the stress of a ticking clock, it is so easy to swap the master keys. Just remember the correction. When solving for c-squared, the ellipse uses a minus. So c-squared equals a squared minus b squared. The hyperbola, on the other hand, uses a plus. So c-squared equals a squared plus b squared. Trapdoor 2 catches countless students every single year. The tangent sign flip. Just like the standard equations flip signs, the tangent conditions flip right alongside them. If you're calculating tangent c on an ellipse, you need a plus b squared at the end. For a hyperbola, you absolutely must use minus b squared. Seriously, do not let this easy point slip away. Now, trapdoor 3 is mathematically fascinating. Phantom circles. It's super common to just assume a hyperbola always has a director circle just like an ellipse does. But mathematically, if you look at the formula, if your a value happens to be less than your b value, the right side becomes negative. That means the radius is imaginary. The director circle literally vanishes. Poof, gone. So, having navigated all these traps and mapped out the high-yield zones, let me ask you a crucial question. If you had to strip away everything else the night before your test, what is the singular framework, the absolute minimum DNA you must hold on to survive? Well, this is it, your ultimate survival guide. Take a mental snapshot of this core mathematical DNA. See how the ellipse DNA strictly relies on E being less than 1 and uses all those positive structures for tangency? Contrast that instantly with the hyperbola DNA, where E is greater than 1 and the minus sign completely takes over. Master this interconnected network, trust your visual intuition over rote memorization, and you won't just pass the exam, you are going to absolutely dominate it. The real question is, if math is a language, are you going to keep memorizing the vocabulary, or are you finally ready to just speak it fluently?